All right. Well, happy St. Patrick's Day for all of you that are Irish or just pretend to be Irish on today. Um, Welcome to another great day of calculus. We're near the end, right? We just got a couple more sections to go here, and we're going to be wrapping up. But the plan today, you may have noticed that we skipped over 4.2 kind of in the process of how we are going. So we're going to backtrack and kind of knock that out. And then we'll see where we stand after we talk about that section. But before I get going on that, are there any questions you guys have on homework or anything else we've talked about?
Can we do 4.2 number 7?
Possibly. Since we've
It's a
skipped.
Euler's method question. I know it's a little long. I tried to solve it like 3 times last night.
Okay, well then, Susanna, since that's it's actually pronounced Euler's method, but
Oh, Euler's,
it's all
sorry.
good. But since that's an Euler's method problem, and we haven't talked about that yet, let's hold off on that. I'm gonna talk about Euler's method today, and what we can do is we can go back and look at that one as an example.
Yeah, you could do it at the end of class. That would be great.
Yep, totally. I'll put
Yeah,
that on my list and remind me if I kind of forget about it.
okay, I'll just put it in the chat right now then.
All right. Are there any others that people would like to look at? So errors number 8 or 9. Is that the same deal? Are those both Euler methods as well? Yeah, okay. Well, I think when we get to Euler's method, it will make a lot more sense. That's one of those things where if you try to do it without having seen it, you're like, what the hell are we doing? But it should make sense after we do it. Okay, so we'll come back to those after we talk about what Euler's method even actually is. So, all right. Okay, well then I'm going to go ahead and get going. I'm actually not going to hop up to the whiteboard just yet because what I want to show you or what I want to talk about is going to involve the calculator a little bit. But here's what we've talked now a little bit about differential equations. The whole idea is we're trying to find a function that satisfies the given equation. And we know how to handle some of them. We know how to deal with ones where we have y prime equals a function of x, because that one we just integrate, right? And we also know how to deal with the ones that are separable, where we can move all the y's to one side, all the x's to the other side, and then we can integrate both. But the problem is that there are lots of differential equations that don't have either of those forms, right? Where we don't have just x's, so we've got both x's and y's, but we can't split them apart. So the question is, what can we do about finding solutions to those? Now, we're obviously not going to go really deep into this because there are entire classes that are called differential equations, right? Like I think I told you, if you stay in our sequence, you'll be taking that next spring. That's where that one shows up. So we're just going to do real top level. But what I want to talk about today are ways of actually making a guess, making approximation, making this is sort of what this might look like. And that's what, like, Euler's method, for example, is one of those. So we're going to look at how do we make a guess if we can't actually do one of our techniques. But what we're going to be looking at is primarily what happens when we have an initial value problem. So when we find a particular solution. Remember the difference? General solutions. General solutions are the ones with the plus c's. They're the ones that we don't know exactly which function, but we know that it's one of a certain form. But then if we know something about that function, so we call that an initial condition, then we can get the particular. So it goes from this big class of functions down to the one. And things like Euler's method, those things allow us to find solutions to the particular solutions to differential equations. So the first thing I want to show you is what we call a direction field. and how we can use direction fields to help us out. So I'm going to go ahead and share my screen and show you this guy. This is I basically just did a Google search for direction field plotter. There's a bunch of these out here. But let me just show you how this works. So first of all, you'll notice here that we're going to write it as, they have it as dy dt, same thing as dy dx. But these are going to, this field, this direction field plotter is going to allow us to do this for anything that we can write as y prime equals, but it has to be first order. Okay, so first order, hopefully you remember what that means. First order means there's just a first derivative in our differential equation, and there isn't a second or third or anything higher. All right, so this one, for example, is just y prime equals x. Now, y prime equals x, you could solve. Right, let me actually go to a whiteboard and show you what we're actually doing here. So we've got the differential equation y prime equals x. Let's go ahead and solve that real fast. We notice that this is only in terms of x, so all we have to do is integrate. So we get y is equal to x squared over 2 plus c. So just think about what these are going to look like. This is our general form, but our particular form, now we'll just substitute values in for c, right? So this is general. But let's say I gave you an initial condition, and I said that y of 0 was equal to 1. Right? We know that we just go ahead and plug in the 0 for x, the 1 for y. That allows us to solve for c. And so this guy would be a particular solution to the initial value problem where y of 0 is equal to 1. All right, what does this look like? What's the graph of this particular solution going to look like? What shape is that?
Parabola, because of the square.
Yep, there you go. So it's a parabola. It's a happy parabola because it's plus 1/2 x squared. The 1/2 flattens it a bit. And then what's that plus 1 do?
Shifts it up 1.
Yeah, it just shifts it up 1. Okay, so what that's going to look like is something like this, right? So this particular solution looks like that. Now, let's come back and look at the general solution. Suppose we had a different c. Instead of a 1, let's say that was 5. Or it was -2. Or it was, pick your favorite c that's not 1. What's that do to this graph?
Depending if it's positive or negative, it's just a different shift.
Yeah, it's just a different shift. It either shifts it up or down. So we might have this one, or we might have, well, that one got a little flat. This one, or we might have this one, right? So the only difference here in our particular versus general is where this guy is located. And when we have an initial condition, it basically just tells us which of all these very many graphs are we on. Okay, so this one's easy to solve. We got it. Now, let's go back and let's actually look at that direction field map. This guy right here. So first of all, let me explain what all these different arrows are. These arrows are showing you the tangent line at these given points. So think about this differential equation. We have y prime equals. What this is doing is it's telling us how to get the slope, right? That's what y prime is. It's the slope of the tangent line. So this is telling us how to get the slope, and it just says that the slope is equal to the x coordinate. So if we were to come, let me just scroll down a bit so we can actually see the axes here. There we go. So let's just like come over here where this is, well, let's go in between these two. So between 0.5 and 1 is 0.75. So this arrow right here has a slope of 0.75. And it's positive, and you can see that it's sure that's around 3/4. And notice that all of these arrows, no matter where we are on this same x, all have the same slope, because our differential equation is telling us that the slope is equal to the x coordinate. If we move further out, like come over here, this is 3 1/4. Notice that it's a steeper line. It now has a slope of 3 1/4. But again, all of those x's have the same slope. So as we move to the right, the slope gets bigger because x is getting bigger. When we're near 0, notice that it's getting flatter, like it should. Now we go on to the other side, and the arrows are now pointing down. The lines are slanted down because we have negative slopes. Our slope is equal to x again. But we have the same deal where if we were to run up one x value, our slopes are all identical. So this is all a direction field is. It's a graph of tangent lines, or at least portions of tangent lines for all the different locations in our graph. Okay, so what? Why do we care about that? What does it do? Well, let me show you. So I'm going to stop sharing here for a second because I need to take a screenshot. I'm going to go ahead and just copy the screen and put it somewhere where I can play with it a little bit. Okay, so let me go ahead. Now I'm going to share my screen again. All right, so all I've got here is I opened up a paint window so I can actually kind of draw and stuff. But here's what I want to show you. Suppose that we want to start drawing a solution to one of these things. All right. And let's go with an initial condition. Let's say that we've got an initial condition, like I told you, y of 0 equals 1. So y of 0 equals 1 tells me that there's going to be a point right here. It's not letting me draw. Hold on one second here. Oh, never mind. Don't mind me. It's early morning. I had all your pictures covering up the thing, so let me do what I want to do. All right, anyway, so we've got a point right here, right? There's our y of 0 equals 1. Now, let's think about what's going to happen if we move away from there. Like right now, we know that that slope is 0 because y prime equals x. The x coordinate is 0, so the slope is 0. So that would suggest if I was going to move on a line that has slope 0, I would go to the right. So I just go right and left. So I'm just going to draw a little line segment here. That's right and left. Okay, you can't see that yellow probably. Let me make it a little bit darker. All right, now, what happens if I get over to the end of this line segment? Now my slope is slightly positive, right? The slope is going up just a little bit. So let me draw a little line segment that has a slope that's slightly positive. Now I get here, my slope gets more positive, gets more positive, gets more positive, gets more positive. And notice what shape I'm starting to see here. Well, if I go the other direction, think about how those slopes are now negative. So I do have to still go up, but just up a little bit in the other direction. And what shape do you see? Well, you see that parabola. You see that shape that we were getting matches what our solution is when we do the calculus. So this is how we use slope fields. Slope fields help you picture what solutions are going to look like. Now, once you see a lot of these, you can get really good at it. Basically, just kind of follow the arrows. And so if I were to start anywhere, let's say my initial condition, instead of being at 0, 1, was, say, over here. Let's say this is where my initial condition is going to be. Well, follow the arrows. I'm going to go down this way, but as I go this way, I get flatter. And then as I get on this side, I start getting steeper. And so there would be the graph of the function that satisfies the initial condition of whatever this was, probably like -4, -2. All right, so really what we want to be able to do is use this for things that are not solvable for us, right? Like the y prime equals x we can solve. So this was sort of silly in terms of using a slope field to help us, but we could have something as simple as this. Let's change this. So instead of just x, it's say x plus y. All right, so looking at the slope field, if we do y prime equals x plus y, let me go ahead and graph it again. So you notice this one looks considerably different. And that's because this is a different differential equation. This is one that we cannot solve. We don't have the tools to be able to solve this one. But we can still get an idea of what the solutions will look like given an initial value. So let me show you how this would work by going over to Paint so I can draw on it again. So give me 1 second again to get this guy set up. All right. Let me share that again. All right, so here is this slope field, right? This direction field. You keep hearing me say slope field, even though the book calls them direction fields. They're the same thing. I learned it as slope field. I think that's more descriptive because these arrows are your slopes. You're going to learn later this thing called a vector field, which is really looks like this as well. So there are all kinds of fields like this. So if you hear me say slope field, it just means direction field. All right, so here's what I'm going to do. I'm going to show you some solutions. We're going to graph some solutions to this, some particular solutions. Even though we won't necessarily have a formula, we'll at least know what their shapes look like. So here's going to be my first initial condition. Let's say that I'm starting right here. Except I need to actually draw. I forget where I was, so we'll say that we're right here. All right, now let's just kind of follow the arrow. So this arrow tells me to go up to the right. I'm going to go up to the right. Now I get over here, it starts getting steeper up to the right, steeper up to the right, steeper up to the right. So it looks like I do something like this. Now, if I go the other direction, notice that this gets flatter and then eventually turns negative. So it looks like that right there is the graph, or approximately the graph, of the solution to the initial value problem that gave us this initial condition. So all I'm doing is I'm following the arrows. So let's do one over here. This one's got a pretty steep going up. So I go up pretty steeply and I get even more steep. It does something like that. On this side, it flattens out until eventually it turns negative slope, and I don't know, does something like that. So there's another solution. It's another solution, but it's a particular solution that went through that point. I'll do one more for good measure. How about I'm down here? Now these slopes are pointing us downward and getting steeper. On the other side, they're always pointing downward, but they don't really flatten out much. So it's going to look like that. So there are 3 different solutions to this differential equation, 3 different particular solutions. And the particular solutions were determined by our initial conditions. Let me mark those in black so you can kind of see where we started. So for lots of differential equations, your initial condition will give you a completely different shape. That first one we were looking at, the y prime equals x, every one of them was a parabola. This one, this is y prime equals, I think I did x plus y. Notice that this one, the solutions, the shapes change dramatically depending upon where we started. All right. Okay, so this is the idea behind direction fields. Let me show you another one, because this one's going to get at the topic I want to talk about. Let me change this so that this is a function only of y, that there are no x's in here at all. So let's do this. We're going to do 0.1 times y squared times y minus 3 times y plus 2. So I just chose this because it's going to show me what I want. The 0.1 makes it so that we can actually see the arrows kind of decently. All right, so here's the differential equation, y prime equals all this. Now, it turns out this one we could solve. We actually can find the solution to this because it is separable. We're not going to because it's going to require some partial fractions and it's kind of gnarly. I just want to draw the graph of the direction field. And kind of like that first one, notice that this one only depends on y. So if we were to go across at one specific y, all of those arrows point the same direction. All right. Well, we could do the same thing that we did before, which is we could draw some solutions given initial values. And it basically is the same idea as before, which is follow the arrow. So let's do that. Let me go ahead and get this guy ready again. Because you're going to notice something interesting, I think, when it comes to the shapes of the solutions, the particular solutions. All right, so here we go. Here's this guy again. Let me pick a color. All right, so here's going to be an initial condition. So how about we start right here? So let's look at what that slope's telling us to do. It's telling us to go down. And as we go down, it's going to flatten out. So we're going to kind of flatten out until it looks pretty darn flat, right? Like a horizontal line. So there would be one. Now, if I go the other direction, I'm going to, again, flatten out. And it's going to do something like that. So there is a solution to this. Let's pick a different initial condition. Say something up here. All right, no, let's go down here. Let's do this one. So this one's telling us to go down. But again, it sort of flattens this out. So we go that way. If I do another one, say down here, this tells me to go up real quick, but then flatten out. I guess let me continue it down. So boom. Let me continue this one out, flattens out. And then I'm going to do one more up here. Let's say we're at this point. That's going to just fly up and then kind of flatten down. So here are a bunch of our solutions, and you'll see that they have very different shapes depending upon where we started. But notice that they all have horizontal asymptotes. Every single one of these graphs, regardless of what color it is, has a horizontal asymptote of some type. There's the one that's right here. All right, there's one at the axis, so it's 0. And then there's another one at this point, right? So this was at y equals 3. This was at y equals 0. And this was at y equals minus 2. All right, now I didn't actually copy the differential equation down onto this, so let me just go ahead and write that out for you. So that was y prime equals, it was 0.1 y squared times y plus, uh-oh. It won't let me write over there. There was a y plus 2 and a y minus 3. Let's ignore that. So check out what's special about these numbers, 3, 0, and minus 2 in terms of this differential equation.
Is it that they're on opposite sides, like one's positive, one's negative, but then because you have to square it?
You're making that way too complicated, Susanna.
Sorry.
No.
It's just like the factors of the formula we're given.
Yeah, they're the zeros of this, right? If you think about what happens when you plug in 3, 0, and minus 2, 3 makes this 0, so we get y prime equals 0. Minus 2, same story. 0, same story. These are the values that make this guy 0. So think about why that's significant. What happens when you have y prime equals 0? Well, your slope is 0, which means your graph is flat, right? It's horizontal. And that's what we're seeing. As we get closer to those y values, these things flatten out. You can even see that just in the arrows, right? Look at the arrows on here. As we get closer to those places, they end up flattening out. And so we have a name for those. Those are called equilibrium solutions because they're making it so that the function doesn't change. Y prime equals 0 means that your function is constant, at least momentarily, right? So those are what we call equilibrium solutions. So let me go back to the whiteboard here. Let me write this out for you. All right, so equilibrium solutions. These are the places where y prime equals 0, so y is constant. So basically that just means that if you're there, your function doesn't change. So what that leads to are asymptotes or horizontal lines. And we classify them in three ways. There are 3 types of them. They're what we call stable, unstable, because if you've got stable, you can have unstable. And then the third one is called semi-stable. All right, so think about those words and what they mean, and this should kind of make sense. Stable suggests that that equilibrium wants to be that way. Unstable means it doesn't. Semi-stable means, well, it kind of does, but it kind of doesn't, right? It's a little bit of both. All right, well, let me show you how you can tell which is which on a slope field. All right, now, basically the way to think about this is stable means that if you leave it, you come back. Unstable means if you leave, you go away. And semi-stable means if you leave, you either come back or go away, depending upon which way you left. Now, I can give you a physical example, like a real life example, to help you kind of understand the difference between these. So I want you to think about a bowl and a marble. All right, so suppose that I've got a bowl. All right, so you got your cereal bowl for your breakfast this morning. And in that bowl, we have a marble. Now, there is an equilibrium place, which would be at the bottom of the bowl. If you put the marble in the bottom of the bowl, it's just going to sit there, right? Now, what happens if I were to move that marble up the side of the bowl a little bit and then let it go? What's it going to do?
Wouldn't it fall back down?
Yeah, it's going to roll back down.
Unless you roll with enough force that it bounces out.
Right, but we're going to assume that that's not what's happening here, or make this bowl infinitely deep so we don't have to worry about that. But if I just pull it up a little bit and then I let it go, it's going to return back to its spot. Yeah, it's probably going to roll past, but eventually it'll oscillate and it'll stop moving. It'll be back in that bowl. That's an example of a stable equilibrium place. Because no matter which direction I were to move this in the bowl, when I let it go, it's going to roll back to where it was. All right, now to make this unstable, all I got to do is turn that bowl upside down. And now let's put the marble on the top. So if I've got my bowl upside down and I just set the marble there, it's in equilibrium. It's not moving, it's just going to stay put. But now what happens if I move it a little bit over to the side? Well, it's just going to roll away off of that bowl. So it's not going to return to its initial position. That's unstable. All right, so that's what I mean with if you leave it, you come back. So with stable, if you leave it, you're going to return back to that initial position. If it's unstable, if you move off of it, you're going to continue to move off of it. You're going to go away. All right, so hopefully that kind of makes sense, stable and unstable. And then semi-stable means that it depends which way you're going. Oh, and errors, I just saw you put in the chat box, pendulum. Yeah, pendulum's another really good example of a stable equilibrium, right? You got a pendulum that's going back and forth. If you're at the bottom, that would be stable equilibrium point. If you were to move it off a little bit and let it go, it's going to eventually come back down and return to its initial spot. Okay, so semi-stable needs to be one where sometimes we come back, but sometimes we go away depending upon where we are. And a good physical example of this for those of us that live in the mountains would be a mountainside that looks sort of like this. Let me, hold on, let me exaggerate the flat spot. All right, so let's say that you're on a mountainside here. Now, if our marble was at this position, it's in stable, it's in equilibrium. Now, what's going to happen to it when I move it depends which way I move it. If I were to move it up here, it's going to roll back down to where it was before. So on that side, it's behaving as if it's stable. If I were to move it the other direction, instead of rolling back to where it started, it's going to roll off on down. You may remember in Calc 1, these were critical points that didn't lead to extrema, that kind of idea. Right? But in this sort of situation, this is the semi-stable, because depending upon which way you go, you may or may not come back to where you started. All right, so hopefully that makes sense for stable, unstable, and semi-stable. Now, let me show you what that means in terms of the direction field, the slope field. So I'm going to bring us back to the slope field, the one that I didn't actually draw on. But you can see the equilibria again, right? So there's one at 0. There was the one at 3. And there was the one at -2 down here. Okay, so how do you know whether it's stable, unstable, or semi-stable? Well, here's what I do. I look at, say, let's look at one of these equilibria. Let's look at 3. Now, what happens if I'm a little bit bigger than 3? What are these arrows going to make me do? Are they going to make me go away from 3 or come back to 3?
Go away.
I'm going to go away.
Positive direction.
Yep, I'm going to definitely go away. So in this case, I'm moving away. Now, what if I'm a little bit below 3? What are those arrows going to do?
Bring you back.
Are they going to bring me back to 3 or take me away from 3?
Oh, you're still away from 3.
They're still going to take me away, right? So in either direction, if I'm above, I'm going to continue getting bigger. If I'm below, I'm going to continue getting smaller. So in both directions there for 3, I'm moving away, which means that guy's unstable. That's an unstable equilibrium, because if I move away from it, I keep moving away. Let's jump down and look at -2. So -2, if I'm a little bit bigger, those arrows bring me back down to -2. If I go smaller, those arrows are going to bring me back up to -2. So -2, regardless of which direction I go, either above or below, I'm going to get sucked back in to 2, or to -2. So -2 is a stable equilibrium point. All right, so what about 0? Well, 0, if I'm a little bit bigger, those arrows point down, which are going to bring me back down to 0. If I go below 0, those arrows point down, which are going to bring me away from 0. So 0, it depends which side I go. One side I get brought back, the other side I get taken away. So that one's semi-stable. So you can actually use the arrows to let you know which kind of equilibrium you have. Let me go back and show you the one where we actually drew the picture of the arrows. Hopefully y'all can see that. But I want you to notice what happens with the different equilibria in terms of the asymptotes. We saw that y equals -2 was stable. And notice that when we were below and when we were above, we approached that asymptote as we went to the right, as we went towards positive infinity. And that's the case with stable equilibria. You're going to approach those as you go to infinity. The unstable, notice that as we go to infinity, we're peeling away from them, but they were an asymptote as we went to negative infinity. And then the semi-stable, they had an asymptote on either side, again, depending upon which portion we had, whether we had the stable side or the unstable side. All right, so these show up a lot in these kind of differential equations, the ones that only have y's as your, or where your differential equation is y prime equals a function of y. They're called autonomous. You don't have to write this down, but just so you know, those are called autonomous. It's spelled autonomous, but autonomous differential equations. Those have equilibria solutions, and it really is just as easy as finding them as just looking at the equation itself and finding the zeros. All right, so that's kind of cool. But take these for what they are. They're a way of visualizing what the solutions are going to look like. And they can literally look like anything. I mean, let's just sort of play with this real quick. Let me change this to, say, y times sine of x. Graph this one, and I'm sure it's going to come as no surprise to you guys that there's a little bit of oscillation stuff going on in this. Think about what these solutions are going to look like. If I were to start over here, I'm going to go up, get flatter, then I'm going to come down, get flatter, then I'm going to go up, get flatter, come down, right? We start seeing something that looks cyclical, looks kind of like sine or cosine. There's a little bit of a twist to it, obviously. The fact that it gets steeper the further away from the axis you are. But this visually, once you get good at reading these, you can see what solutions look like. There's going to be a solution that does that. Or down here, there's a solution that does this, right? So anyway. So have fun with these. What I would do to get comfortable with these is go to one of these plotters, draw a bunch of them, and just play around with drawing the pictures, remembering that these are tangent lines. These are tangent lines to the curve. So it's almost like we're back in first quarter, where we're given a bunch of tangent lines, and we're seeing what does the graph actually look like. Okay, so those are direction fields. And again, it's just a good way of approximating your solution. But what we probably really want to talk about is Euler's method, especially since there were some homework questions about that. So before I bounce back to the homework questions, let me go up to the whiteboard and we'll talk a little bit about Euler's method and what it's doing. All right, so I'll be right back with you. All right, so now what Euler's method is a numerical way of getting the solution to differential equation that kind of uses the idea of the slope fields. All right, where we're going to use whatever the derivative was to help us get the next bit of our function. So I want to go back to that one that I kind of started with the slope field idea. The y prime equals x plus y. And I want to give you an initial condition. All right, so let's say we're going to do y of 0 equals 1. So we're going to find a particular solution to this guy. Now, Euler's method's not going to get us an exact solution, but it's going to give us an idea of what this solution should look like. So this is really numerical, like lots of calculation with our calculator and everything. But here's the general idea of Euler's method. So we're going to start at our point of y of 0 equals 1. So there's our initial value. So what I'm going to do is I'm going to calculate the slope at that point. I'm going to use the differential equation to help me get the solution, right, to get that slope. And then what I'm going to do is I'm going to use that slope to take a step over to the right. Okay. So let's start by finding the slope at this point. So I'm going to make a big T-chart kind of thing. It's actually not going to be a T-chart. It's going to be a pie chart, because what I need are x, y, and then I need my slope. Okay. So I'm starting at the point 0, 1. And if I go up here to my differential equation and tell me y prime is equal to x plus y, I'm going to take 0 plus 1 and get 1. So that means that right now at 0, 1, the best approximation for our function would be the line with slope 1. So this is the tangent line at that point. All right, so here's what we're going to do. For Euler's method, we're going to take a step to the right. How far we're going to go to the right is up to us. Just for the sake of making this easier for me, I'm going to make it a step of 1. All right, so I'm going to come over here 1 step. So if I were to follow the idea of this slope, since the slope is 1, that means I'm going to go up 1. So what is that new point? What are the coordinates of this point right here?
Would it be 1, 2? I mean,
Yep, it's
or
exactly 1, 2. All right, so we went from 0, 0 up to 1, 2, because we're just following the tangent line. Using the tangent line as approximation, just like we did back in first quarter.
0, 1, not 0, 0.
Yeah, it says 0, 1, but
Okay.
thank you. All right, so we went from 0, 1 up to 1, 2. All right, so now we're just going to do the same thing at this new point. At 1, 2, I put this into my y prime. I'm going to get 1 plus 2 is 3. So now I get a slope of 3. So that means that the tangent line here is going to have a slope of 3. So that's going to be much steeper. But let's do the same thing. Let's go over 1. How much am I going to go up now?
3.
There you go. It's just the slope. So I'm going to go up 3. So that's going to bring us to a new point. And that point, of course, is going to be 2, 5. All right, well, now let's do it again. So now I'm at 2, 5. Add those together, I get a slope of 7. All right, well, that's going to get really steep. But you see what's kind of going on here is I'm getting little line segments that are creating my curve. Now, I can go the other direction as well. Let's go backwards. So if I were to go backward 1, I'd have to go down 1, which would bring us to the point -1, 0. So let's see what happens when we plug those in. So I get -1, 0. Adding those together gives me a slope of -1. So at this point, I would need a slope of -1. So I'm going to be on that line segment. So again, if I go over 1, now I'm going to go up 1. And that brings me to the point -2, 1. All right, well, let's plug those in. So -2 plus 1 is 1, or sorry, -1. So I'm still going to have a slope of -1, which means I'm going to keep going in that direction. All right, so I know that this is kind of messy and dirty, but let me replicate the same picture over here so you can see what we just did. We now have a graph that's just a whole bunch of line segments. I'm going to just color them all the same color. But we had this one, followed by this one, followed by, I didn't draw the next one, but it's going to be steeper. And then we had this one, and there was going to be another one that looks like that. Okay, so this is the collection of all those line segments. That's an approximation for what that solution looks like. Obviously, the solution is not going to be line segments. It's not going to be like really angly. It's going to be more curved. But this is approximately what it looks like. So this is the idea behind Euler's method. You're just using those tangent lines to get you to your next point. Use that next point, plug that into your slope field to get your next tangent line. So you can follow that to get your next point, to plug into the slope field and differential equation to get your next tangent line, and just repeat the process. Now, what would make this a better approximation? What would make this little disjointed line segmenty thing a better picture of the actual solution?
Smaller increments.
It's almost as if we've done this before. Yeah, if you haven't figured this out yet about calculus, it's all about take this kind of simple idea and run with it infinitesimally small, right? So instead of doing things that are length 1, what if we went length 1/2? That would give us smaller line segments, shorter line segments that would then better fit it. All right, well, 1/2, well, what if we make it 0.1? What if we made it 0.01? And the smaller we make those steps, the closer that approximation is going to be to our actual solution. All right, so how do you feel about the idea behind Euler's method? Does it at least make sense? I hope, because it's literally the same thing we've done forever in calculus. We are approximating the curve with line segments. We've done that. We did that when we did arc length. We did that when we did, well, really anything, right? And we make it a better approximation by shortening them, making them smaller. All right, so clearly, this is just going to get more complicated if our function is more complicated, but the process is exactly the same, right? So let's actually run with the same one, but let's shorten the step. I'm not going to shorten it too much because otherwise I can't really, well, let's just do this. Let's make it so that we take steps of 1/2 instead of 1. All right, so we're going to make our little t-chart here again, our pie chart, I guess. And we're again going to start at 0, 1. But now let's take steps of just 1/2. All right, so here's how this is going to play out. We're going to do exactly the same thing. I just noticed I'm drawing in the glare there. Let me close my shade so if we can see it a little bit better. All right, so let's kind of follow the process. Again, at 0, 1, we have a slope of 1. So that means that we're going to go over 1/2, up 1/2. So I'm going to change the color on it. Hopefully you can kind of see against the purple. I'll make it kind of a, let's go make it orange. You should be able to see, differentiate. Okay, so I'm going to come up here again to 1/2, 1/2. But now here's where I'm going to diverge. Because now, if I go up 1/2, my y is 3/2. Right? Because I was over 1/2, go up 1/2, 1.5 is 3/2. So if I do 1/2 plus 3/2, that gives me a slope of 2. So now I've got a bit steeper of a line. If I go over 1/2, that's like going up 1, which is going to bring me here. And so now that's the point 1, 2. Something is going on with my graph because that should be that same point. Oh, no, because that's not 2, it's 5/2. There we go. All right, so what I did there, let me write it out for you, is I was at 3/2, but I'm taking a step of 1/2 times my slope. So that's 3/2 plus 1, which is 5/2. There we go, that's better. All right, so my slope for this next one is going to be 1 plus 5/2, which is 7/2. So my new y value is going to be 5/2 plus 1/2 times 7/2. So 5/2 plus 7/4. That's 10, 17/4, which is 4 1/4. So that's going to bring me up to 4 1/4, which is like here. Let me go the other direction. So when we were at 0, 1, I'm now going to subtract 1/2. So I'm going to be at this point right there, which is minus 1/2. Adding those together gives me a -1. So now I need to add 1/2. So that's going to bring me back up here. And so on, right? So notice what happened is I'm getting a similar shape. It's not identical, but this new one, this orange one, is going to be a closer approximation to the actual solution. All right, so Euler's method, smaller steps means it's going to fit better. All right, so let's go look at one of those from the homework that you guys were asking about. And let's see if we can kind of put this into play so we can get an idea of what the solution is actually going to look like. All right, so I'm going to bounce back to my computer. I'll be with you in just one second. All right, so I'm going to go ahead and share my screen, and we're going to go back to that, to the homework. And let's go take a peek at, I don't remember, oops. Sorry about that.
I think 7, 8, and 9 were all Euler's problems, so just one of them, I think, for me at least, would be okay.
All right, well, let's go pick one of those to go look at. All right, now that I've gotten everything figured out here, there we go. Okay, so let's go look at Drake and Field's numerical methods. And we'll go ahead and go with lucky number 7. It doesn't really matter. Okay, so we're going to use Euler's method. And it says with step size 0.5. All right, so that just means we're going to go a step of a half each direction to get our next values. And it says, so we want to approximate the y values, y1, y2, y3, and y4. So that just means the ones that we get next, right? So y1 is going to be the first one that we calculate. Y2 is going to be the next one we calculate, and so on. We're given the differential equation. So we have y equals -2 minus 3x plus 4y, and then we have an initial condition of y1 equals -4. All right, so let's go to the whiteboard and let's actually work this out. All right, now we're not going to graph it right away. We're just going to calculate. But then once we calculate it, we'll kind of draw the points and see what it looks like. All right. So let me write down what we had. So our differential equation is y prime equals -2 minus 3x plus 4y. And our initial condition is y of 1 equals -4. All right, so let's make our little chart again. So we're going to have x, we're going to have y, and we're going to have y prime. We're going to start at 1 minus 4. And then I'm going to go ahead and fill in the x's. And I can do that right now. I know exactly what x's I'm going to have because they told me to use a step of 1/2. So my next one's going to be 1.5. And then we're going to be at 2. And then 2.5. And then at 3. And I believe that that's as far as we need to go because they said to get y1 through y4. So this is going to be y1, y2, y3, y4. All right, so let's start with the derivative. At 1 minus 4, y prime is going to equal -2 minus 3 times 1 plus 4 times -4. All right, see you, Bruno. So this is going to be, let's see, -2 minus 3 minus 16, which is -21. So our slope at that point is -21. So before we move on, are we all good with the first slope? Just a matter of plugging it in. All right, so now let's get our y1. So y1, oops, not y prime. Hold on a second. All right, y1 is going to be -4 plus -21 times 1/2. So the -4 is where we were. The -21 is the slope we found. And then the 1/2, that's our step. Right? Actually, I'll make it clear as day because we were told our step was 0.5. So maybe I'll just write it like that. So that's going to give us -14.5. So that's what's going to go right here. So there's our next point. And now we're just going to repeat the process. So y prime here is going to be -2 minus 3 times 1.5 plus 4 times -14.5. So that's -2 minus 4.5 minus, let's see, 58. which is negative 64.5. So to get y2, we're going to take the y where we were, negative 14.5, and we're going to add to that negative 64.5 times 0.5. Okay, well, I'm getting to the point where I don't want to do this in my head, but I think I can get this one. So 32.25, so minus 46.75, he says with a question mark in his voice. I think.
Yeah, you're right.
All right, cool. Thanks for that confirmation. All right, so there we go. So now keep going. So the next y prime is going to be minus 2, minus 3 times 2, plus 4 times minus 46.75. And I'm officially bored and tired of this. And I think you guys are probably bored and tired of seeing me do this. But you see the process. So at each new point, we calculate the slope. Then we use that slope with our step to figure out our new y value, and then repeat the process. So this is the kind of thing that computers love to do. Computers love having real systematic, repeat the process kind of things. And so Euler's method is actually how a lot of calculators, especially back in the day, like the early graphing calculators, like the ones that, you know, were coming out in like the 80s and 90s, those use this kind of idea of how to draw graphs. I'm not sure if the more sophisticated, like the TI-89s and these other ones that have computer algebra systems, if they still do it this way. But, you know, if you just make that step size small, especially on a screen like a calculator screen, you're not going to be able to see the difference, and it's going to look like a smooth curve. All right.
The problem with the homework was the first time I tried to follow the video, I got like 2, because you had to put, they give you like y1, y2, y3, y4, and you don't input it one at a time. You input all 4 at one time. So like to get to get y4, you need to get y1, 2, and 3 right. But if you accidentally like mess up in like the algebra, then like it's possible to still get like y1 correct, but you could get y4 wrong if you mess up like multiplying or something.
Yep. Well, and even like the way I'm showing you, same story, right? If we make a mistake anywhere, like let's just say I made an error right here. So instead of minus 21, let's say I calculated, I screw up something and I go minus 20. Think about the impact of that. That minus 20 comes over here, which changes this to minus 14. That minus 14 comes over here, which changes this number, which changes that number, which changes this one, which changes that. So yeah, one mistake anywhere and you're toast, because everything is built on the previous step.
Yeah, because this looks very familiar to what I tried to do yesterday. But for some reason, I just kept not getting all 4 right. And I was like, and then every time they would give me a different question. So
yeah.
But so I think I get it now a little better.
Go slow with these. Definitely go slow, because one little mistake is going to cause problems forever. So take your time, but realize what the process is. And in fact, let me just kind of write down what I did here. We'll make the recipe. Okay. So the first thing you're going to do is you're going to plug the point into the differential equation. And I'm going to put here to get the slope. Okay. Then what you do is you get your new y using, and I'm going to put here y equals, or how about, let's say yn plus 1 equals yn plus the slope times delta x. So the slope that we just calculated is that m. The delta x is the step length that they tell you to use. And then the yn, that was just the previous y value, right? So that gets you your new y. And then, I don't think I've shared with you this. Then you're just going to shampoo. And you might look at that and go, what the hell is he talking about? This is a
You'll rinse and repeat, right?
Exactly. Yeah. You look, what are the instructions on a bottle of shampoo? I think it's funny that there are instructions on a bottle of shampoo, but it says lather, rinse, repeat if necessary, right? Or repeat if desired. Well, yeah, shampoo just means do it again. Right? So it's just same thing, same thing. So it's really procedural. It is what the epitome of what I call monkey math, right? You can train a monkey to do it. It's just, all right, monkey, plug the point in, get the slope. Okay. Now use the slope and do this. Okay. Do it again. Okay. Right. There isn't, and please don't take this wrong because I don't mean it this way, but there isn't thought involved, right? There really isn't. This is like muscle memory can just take over and you can just go through the process. Right. Yes, you still have to pay attention and you have to make sure you're putting the right stuff into the calculator. Make use of your calculator. Oh, good Lord, make use of your calculator because these decimals can get gnarly as you go along, depending upon what the differential equation looks like and what your step is like. Right. Like that first example I showed you where the step was 1, everything was nice because we just got whole numbers the whole time and it wasn't that big of a deal. But you can imagine if your step was like 0.1, you're going to get into the decimal world very quickly. Use a calculator to help you out. All right, totally do that. But that's the process. And the only thing that changes is you might have a different differential equation, or you might have a different starting point. Okay, whatever. Different starting point, plug that in instead. Different differential equation. Okay, that's the formula you can use to get your slope. But yeah, this is the process. So it's really procedural, which is nice. You just go through the motions and everything's good. All right, so are we feeling better about Euler's method now that you're kind of seeing the process? And specifically, I'm going to ask those of you who asked about it. I know, Susanna, you were one, and I think, Eras, you were the other. But we feeling better? Yep. Okay, cool. Anyway, so it's like anything. It's an approximation. Are the actual y values going to be these if we were to actually find the solution? No. No. The solution is differential equation, and this one is, you can solve it. It is possible to solve it. The solution to this one will not give you these y values for x equals 1.5 and 2. But it's an approximation, and at least we have an idea of what's going on with this function. Like what I can tell you right away is that this function is going to keep getting really big negative. Because think about what's going to happen as we calculate this slope. Now that we have negative 46 here, you multiply that by 4. That's on the order of negative 180. Adding this stuff, we're around negative 190. So you've got a slope of negative 190. Man, that's going to drop you fast. And it's just going to keep dropping. So I already know that whatever the solution to this is going to be one that drops towards minus infinity as we're going in this direction. And so I was able to glean that just from a couple of points. And that's sort of the idea here, is that we can do a little bit of just computation to get a really good idea of what the solution looks like without having to do the algebra and the calculus. So usually we use Euler's method for things that are a little bit more complicated than this, because this one we would just solve. But that's for next year. That's where when you take differential equation, you'll learn the process for solving this one. And it's actually not terrible, he says. Anyway, all right, so cool for that. All right, so we don't really have that much more time because I do have to leave a little bit early because of this all-day meeting I've got. So I'm going to go ahead and stop it here, but I just want to share with you a couple things for what's going to be happening forward. So Friday, we are not going to have class. Unfortunately, my all-day meeting is not going to allow me to do that. So we're not going to have class. You're still going to have a quiz. I did change the quiz start time to 9:30 instead of 8:30. That way you guys can get an extra hour of sleep. If that doesn't work for you, if you're like, no, I want to take it at 8:30, send me a message, send me an email, and I will change it back to 8:30 for you. But I figured I'd give everybody a little bit of extra sleep since we don't actually have to meet class-wise. I think I am going to make a little video that talks about the logistic growth, which is section 4.4. It's a continuation kind of the separation of variables. It's just a specific example. And it is really useful when it comes to population modeling. Like if we're going to talk about how many fish are in Lake Tahoe or how many bear are in the woods and things like that. So I am going to make a video probably, when is that going to get made? Yeah, I might be able to get to it tonight. I don't know, but I'm going to anticipate putting it up sometime on Friday, just so that you guys can see that as an example. But then on Monday, because we do have class next Monday, we're going to kind of just review everything. We're going to get ourselves ready for the final exam. I don't think we're going to cover section 4.5. I'm going to remove that homework from the due dates and all that. So, because that's another thing you're going to learn in differential equations. So that's our plan. The final is a week from Friday, just so you know and can start preparing. Final is a week from Friday. And it will be cumulative, everything up to and including what we're doing here today. So all the way through differential equations. So like I said, on Monday, we'll talk way more about that, try to get you in a place where you're kind of ready for the final and all that. All right.
Just a heads up, and I noticed the final on Canvas is saying it's on Wednesday.
On which Canvas? On the... Okay, well,
Mat106.
No, I know that. I mean, like, where in Canvas is it saying that it's on Wednesday?
Oh, just on assignments.
Okay. Then
yeah, on your syllabus it also says 324.
Oh, it does. Then I guess I have it input wrong on my calendar. It's going to be whatever the syllabus says. So then I guess I lied. It's a week from today is our final. Thank you for that. That was my bad. I misread my own personal calendar. So I guess the final is a week from today then. But anyway, I'll put out, I'll send out a message again through Canvas that's got all this information just as kind of a final wrap up, since we're not going to be meeting on Friday. And I totally apologize for the fact that these all-day meetings are happening this week. What's going on? Actually, I'm going to turn off the recording. I don't need to talk about what that is on the record. Anyway, so I think I'm going to go ahead and stop our recording, and I will see everybody on Monday. Oh yeah, I forgot. There's the quiz on Friday. I should probably tell you what's on that quiz. That quiz is going to cover 3.8, which was, I think it was 3.8, whatever that, the improper integrals, the integrals that go to infinity. And then 4.1 and 4.3 So 4.1 was just your intro to differential equations, and 4.3 was separable differential equations. All right. So Quiz Friday, the last section of 3, and 4.1 and 4.3. All right. Anyway, so have a great couple days weekend, and I will see you all when I see you.